AI is an amazing tool in pathology, and the potential and upsides are huge. They can make a huge difference in patient care. But what when it fails us? What can possibly go wrong, and what can we do about it? How can we prevent it? Well, this video is about it. Recently, I interviewed Dr. Richard Levenson from UC Davis Health, and he is the co-author of a paper titled AI in Pathology. What could possibly go wrong? Well, a couple of things. So if you want to read the full paper, go ahead to Richard's profile, and he has a post about this where he shares the author version of the paper. And when you go there, you're going to end up in Dropbox where you can actually save a copy of the paper. Richard is the last of the paper, and this paper has a lot of interesting insights, but my favorite part is this table, Table 1, Key Challenges, Impact, and Mitigation Strategies in Pathology. This is basically telling you about all the challenges, what is the impact of AI, and what the mitigation strategy. So the challenges are divided in data, model development, and model deployment, because in all of those categories, something can go wrong. When it comes to data, the number one thing is slide preparation protocols. In different medical centers, there are different slide preparation and staining protocols leading to different microscopic appearances. And for a pathologist, it's not a big deal because we just see through it. But for AI, it is. So what is the impact? Well, it can lead to limited transferability of models developed at one center over the other. And how can we mitigate that? We have something called domain adaptation models. We have something called stain normalization to transform images to a similar color domain. Then there is stain randomization to make the model invariant to the differences in staining protocol. And when we assess our AI model, we should always include data from independent test sets from institutions where the slides were prepared different. So that's for stain preparation protocol. The other thing affecting data is image acquisition. What happens here? The image acquisition in digital pathology has not been standardized. Different scanners result in different colors, in slightly different stitching. There are different formats and different resolutions of the image. So what's the consequence? AI model basically can fail to generalize. Model developed on slides from one scanner is not going to perform on slides from another scanner, even if the same glass slides were scanned. So what can we do about it? We can adapt the domains. We already talked about it above. We can also use slide scan on different scanners to develop the model. Another thing that can be done is to standardize micron per pixel, so-called MPP resolution across scanner types when training the model or matching the MPP with the training cohort. And we can also develop a standardized scanning protocol. All these things can help us with mitigating the challenges coming from image acquisition. Another challenge is simply limited pathology slide digitization. Most of the academic centers or even hospitals did not digitize their pathology labs yet. There are independent digital pathology practices up and running, but this is a fraction of the pathology practices in the US and in the world. The standard of care remains the assessment of glass slides under the microscope. What is the impact on AI? The impact is that AI will not have an impact because the models will not be widespread until there is a universal adoption of digital pathology, which is not the case yet. Because there's only limited scanning for routine pathology, if we want to develop AI models, we have to scan archived slides, which is another hurdle on top of the normal pathology workflow. So how could we possibly mitigate that? Well, there must be an incentive model for pathology slide digitization. And the second thing we can do is to train the next generation of pathologists to routinely diagnose digital images. So I'm an example of that. I work on digital slides, and if I was thinking of changing jobs, I would not accept a job where I would have to read glass slides. You can say I'm spoiled, but this is my prerequisite now. I'm, let's say, the next generation of pathologists who doesn't like working on glass anymore. Digital is more convenient to me, and me personally, for my personal benefit, I'm going to be pursuing a career that will require me to read digital slides. And once this shift happens in pathologists' mind, they become a force that drives digital pathology forward. They're going to be creating opportunities for themselves to work digitally, and at some point, there's going to be a critical mass of people who think that way, and it's going to be a snowball effect. So these are the consequences of limited pathology slide digitization. The next relevant problem with data is limited demographic diversity. This is a systematic problem with AI. This is also something that raises an ethical questions. Oh my goodness, AI is so biased. AI is as biased as the data we feed AI, so it's on us to feed it diverse data or make sure that the models we are developing are specific to a specific data set. Let's not expect something that was developed on one data set to perform well on a different data set. For example, white male versus black female, different groups, different data should be used to train models. Why is it important? Because lack of diversity may result in AI models not generalizing, meaning that actually if you apply a model developed on one demographic group to another demographic group, even if it's performing very well on this first demographic group, you can do harm to people in another demographic group. So what can we do about it? Data collection and sharing efforts across institutions around the world. Institutions around the world collaborating. So data collection is one way. There's another way of decentralized learning, training the models in a decentralized way, like federated learning, swarm learning, where the models are trained locally and then a central model is gathering the information. One way or the other, collaboration and data from different demographic groups are the solution here. So once we fix the data problems, now we have to face model development. And what are these? Problem number one, assessment of AI models. Even though the bar for model validation has been increasing, it is still being validated on limited data sets. What is the impact of that? Well, there are differences in validations and they make it difficult to assess the efficacy of the AI model and its impact. If we cannot validate, we cannot check how good it is. So what can we do about it? We can develop standardized assessment protocols specific to pathology. What should they include? First of all, we need data from independent test cohort. We need different scanner. We need to report demographically stratified assessment, and we need to make the code available publicly so that others can reproduce our results and assess it. Once we have that in place, we can think about model interpretability. Currently, the interpretability of deep learning models is still limited. We look at the results. If they're good, but where does the result come from? We cannot derive this information from the model itself. There is a big push for explainable AI, but currently, this is not the default. The default is, let's not argue with results. But why is it problematic? If the results are okay, it should be okay, right? Well, not in the healthcare space, in general, not in any space where decisions about people are being made, and especially about human health, because limited interpretability creates confusion and distrust of AI model. And the healthcare professional community is already very skeptical by default, by profession. The patients also need to trust new technology first before they're comfortable with the doctors, the pathologists using it. So we need explainability. So what can we do to achieve interpretability? We can use so-called introspection tools. We can basically design with interpretability in mind. So using tools such as GradCam, Captum, they are tools used to assess the entire set, and it can use clustering to analyze the similarities in high attended regions across the entire set. But regardless of the tools that you will be using, the message is use a tool and design with interpretability in mind. This is a very rapidly evolving area, and the newly created tools should be used, whether it's going to be GradCam at Captum at the time of you watching this video or something else, or maybe, it's going to be built in whatever framework for model development you're going to be using. Just keep that in mind. interpretability is a must. So once we tackle the problems in model development, what problems will we encounter in model deployment? Well, similar things. For example, protocols for AI model deployment. Because there are few models deployed, there are few protocols for deployment. And the ones that are existing, are they the best? Should we do it better? Should we do it in a different way? We don't know yet. But what we know is that without appropriate protocols, deployment at various medical centers can perform variably with limited downstream impact. So what should we do about it? We actually should do studies and clinical trials that assess different methods of deployment in pathology. Example of things to assess would be, okay, is it best to triage the easiest cases? Is a heat map a good thing to be shown to a pathologist? And if it is, should we indicate model confidence or is it too confusing? Basically, we need to test it, we need to check it. Another thing that can go wrong in model deployment are computing resources. It doesn't apply only to developing countries. Everywhere there are hospitals that basically lack the computer resources needed to deploy AI models. What's the problem with that? Well, even if we have the best AI model on the planet, it will have limited impact if it cannot be deployed. How can we mitigate is to assess AI models that can be run on low-cost computing hardware. When I think about that, I'm like, okay, can something run on a smartphone? Everybody has a smartphone. Does it need access to internet? Maybe not. If it doesn't, then it's better because not all remote areas have access to internet. So for every developed or commercialized, at least commercialized model, the minimum viable hardware needed to deploy it needs to be reported. And there could be also cloud-based deployment in areas where the internet is not a problem, but the compute power is the problem. That could be the solution, and studies would be beneficial. Okay, we have protocols, we have computing resources, but seldom will be something new implemented if there's no incentive. Different kind of incentives, scientific, patient benefit, but also in the healthcare space, the reimbursement models. Currently, there are limited reimbursement models, and in healthcare, without an appropriate reimbursement model, there will be limited incentive to deploy anything. So how can we assess that? We can perform studies to check what the best approach for reimbursement is. I think this is a very comprehensive list. So these were examples of what can go wrong. Are these the only things that can go wrong? Probably not, because as you are watching this video, probably new approaches are being developed and they have new risks. So approaching AI development, AI deployment, AI use with this strategy in mind, okay, what's the challenge? Why is it important? And what are the mitigation strategies for any new AI that comes out there into pathology is crucial. And because you stayed till the end, I know you're a real digital pathology trailblazer. I know you're going to enjoy the full podcast episode that I had with Richard. We talked about AI. We talked about glassless pathology. It's a fun listen. So go ahead, click on the next video, and I see you there.